We're going to briefly talk about graphs. I don't want to talk super long about this, but like for a business pre-calc class, I have to cover it. So let's get into it. Let's look at these two functions. They have some similarities. We're going to look at these two functions in Desmos. I want you to see what you can see. So looking at the equations, you notice they both have a 3, right? This is an exponential function with a base of 3. Here's a logarithmic function with a base of 3. The exponential function has a starting value of 1/2 a times b to the x, and it's tripling every time x increases. And then there's a 2 here. I don't know. Hey, we don't know too much about that just yet. But graphically, we get something really nice. Kind of turn your head on the side a little bit. You seeing some nice symmetry? In math, when we say something undoes something else, that means it's an inverse function. It gives us this symmetry. Every pair of inverse functions, things that undo each other, give us this cool symmetry. So in fact, if I graphed a diagonal line, the orange, the exponential function, is just flipped over this diagonal line of the green. Okay, so basically exponential functions and logarithms, they undo each other. They have a lot of similarities in their graphs. Basically, just whatever happened to the x of one is going to go to the y of the other. We're basically switching inputs and outputs. Okay, so that's kind of where we're going with this. Graphical features of a logarithm are similar to exponential functions. But basically, we're just kind of switching the x's and the y's. Here's what I mean by that. An exponential function has a horizontal asymptote, right? Exponential functions all have horizontal asymptotes. Logarithms will have a vertical asymptote. So there are no horizontal asymptotes. An exponential function would have one. But if we're switching the inputs and the outputs, what's horizontal becomes vertical. There's going to be a vertical asymptote when the input equals 0. I'm going to write this in parentheses too, because if our input's messier, the vertical asymptote will be messier. Where are logarithms increasing? Where is this function increasing from left to right? Well, if we're going from left to right, it's always getting bigger. It's increasing on its entire domain. So it's increasing on the whole domain. This function's always increasing. Just like an exponential function that's an exponential growth function. What was the domain? The domain is all the inputs. We can't plug in 0. We'll get really close to 0, but we can't ever hit 0. So the domain is going to be 0 up to infinity. We can go as far to the right as we want. And the range is going to be all real numbers. And again, remember that this is very similar to the domain and range of an exponential function. We're just switching the domain part and the range part. We're switching the x's and the y's, the inputs and the outputs. It kind of looks like there might be a horizontal asymptote, but there isn't. This function will get as big as we want it to get. Just going to take a really long time. Okay? But there is no horizontal asymptote. Any y value we want to get to, we can get to eventually. As y increases by 1, x gets multiplied by b. That's kind of flipping what we said about exponential functions. Let's not worry about that too much. The larger the base of the logarithm, the slower the function grows. Think about that for long run behavior. What do I mean by that? If the base gets bigger, so let's look at log base 3 of 2x, log base 4 of 2x. Oh, the base got bigger. I said the function's growing slower in the long run, right? Pink is below green. If we did log base 10 of 2x, whoa, that's even growing slower in the long run. The bigger the base, the slower it grows in the long run. Okay? So these are a bunch of properties. Again, we're not going to use these too much, but I got to cover them. We'll use them for this section. Find the domain and range of this function. Well, the domain, again, let's translate that, is when the input is greater than 0. That's a translation of this. The input is x in this case. But in our example down here, example 4, the input is more than x. So the domain's going to be when the input's positive. Well, when is the input positive? Domain is when input's positive. We can't take the logarithm of a negative number or 0. Well, the input of our logarithm in this example is 5 minus 2x. When is that positive? Whoa, blast from the past. Oh my goodness, my arm disappearing. Somebody's going back in time. Is that too old of a reference? Back to the Future? Are y'all too young for that? I don't know. So we need to solve this inequality. Hey, we already did that in this quarter. So we can solve it by subtracting both sides by 5. 2x. Negative 2x has to be bigger than negative 5. And divide both sides by negative 2. And whenever we divide or multiply both sides of an inequality by a negative number, the inequality flips. So negative divided by negative is going to be a positive 5/2, which is 2.5. So the domain is all the numbers that are smaller than 2.5. Our domain is negative infinity is the smallest number we can get, and the biggest number is positive 2.5. But you might say, hold up, Jason. Hold up. I thought you said the domain was 0 to infinity. It's only if the inside is an x. So 0 to infinity is the domain, but the best way to say the domain is all the points where the input is positive. So every time you get messier stuff in here, it's going to mess up the domain. So this part over here is maybe more important. The range, how do we find the range? Range is always the same. I don't care what you're doing to this logarithm, unless you're multiplying it by 0. But basically, range is always going to be all real numbers. That's how we can find domain and range. That's mostly what we're going to do with logs, but you might have 1 or 2 graphing problems, but they'll be simple ones. Match the following functions with their graphs. All right, and there's a couple different methods. I'm only going to go over one here. So let's just talk about one in this video. And that's that property at the bottom. The larger the base, the slower this function grows in the end. Well, that tells us that blue must have the biggest base. Blue is growing the slowest at the end. The blue must be the biggest base. What are our bases here? I only see one base written down. What are the other 2 bases? Well, remember that the common log is log base 10. The natural log, ln, is log base e. What was e again? It was Euler's number. You can always check on Desmos, or you can, Google it. E is about 2.718. So E, we need to know that, about 2.718. Okay, so that's the second biggest number for the base. So this one's got to be F, because it's the biggest base, so it grows the slowest at the end. This is the middle one, G, is 2.718. E is the next biggest. Means this one's got to be H. That's how we can kind of compare different logarithms. Another case is by just trying to find some points or doing some other methods. But we're not going to worry about that too much. Let me know if you have any questions, and until next time.